Modern humans spend 90% of their lives inside tightly sealed, energy-efficient buildings. For decades, the engineering consensus guided how much fresh air those buildings needed. The American Society of Heating, Refrigerating, and Air Conditioning Engineers, or ASHRAE, set a benchmark of 1,000 parts per million for indoor carbon dioxide. But that number was never based on human health. It was established simply to dilute human body odor to an acceptable level. For actual safety limits, engineers look to industrial settings. The Occupational Safety and Health Administration allows up to 5,000 parts per million in a workplace, strictly to prevent acute asphyxiation. We sealed our windows and insulated our walls to reduce energy costs, relying on a comfort threshold for odor and a toxicity threshold for mines and factories. We inadvertently created airtight boxes where an invisible, chronic hazard silently accumulates. To truly understand the modern hazard of indoor environments, we have to follow the air deep down into the human airway. Looking at this cross-section of a blood vessel, we see how your lungs rely on a pressure gradient between your blood and the ambient air. As carbon dioxide builds up in the room, that gradient narrows. Your body struggles to off-gas. CO2 gets trapped in your bloodstream, where it reacts with water to form carbonic acid. This induces a mild state of respiratory acidosis. To keep your blood pH stable, your kidneys have to work overtime, pumping bicarbonate into your system to neutralize the acidity. And the pressure is coming from the outside, too. The Earth's outdoor baseline has risen from 280 parts per million to over 420. Long-term health data from the United States shows exactly how our bodies are reacting. Over the last 20 years, the baseline serum bicarbonate in the average person's blood has risen by 7%. That 7% increase represents a continuous systemic effort to maintain life's basic chemistry. Our internal systems are adjusting for an atmosphere our cognitive centers were never built to navigate. The earliest warning signs came from researchers at Harvard and the Lawrence Berkeley National Laboratory. They designed an experiment to isolate pure CO2 and test its direct effect on different domains of human cognition. They placed knowledge workers in an environmentally controlled chamber. They held ventilation rates and background pollutants perfectly constant, then injected pure CO2 to reach concentrations of 1,000 and 2,500 parts per million. This animated bar chart shows the resulting cognitive test scores. As the CO2 levels increase, high-level executive functions collapse. Scores for strategic planning and information usage plummeted by 50 to 90% compared to baseline. Curious, there was one strange anomaly. Performance on basic, focused activities actually increased. Mild hypercapnia, excess CO2 in the blood, triggers a physiological stress response. The brain hyper-focuses on simple tasks at the expense of broader strategic awareness. At the levels found in typical meeting rooms and classrooms, pure CO2 acts as an active toxin. It specifically targets and suppresses the prefrontal cortex, shutting down our highest-level decision-making centers. Soon after, a research team from the Technical University of Denmark conducted their own chamber studies. When they exposed participants to pure CO2, they found zero drop in basic algorithmic tasks like proofreading or simple math. The researchers identified a dual threat. Pure CO2 suppresses the high-level strategy centers in the prefrontal cortex, but human bioeffluents, the cocktail of volatile organic compounds we naturally emit through sweat and breath, cause systemic physical stress, elevating blood pressure and causing fatigue. In a real-world, under-ventilated room, nobody is breathing pure laboratory-grade CO2. Both threats accumulate simultaneously. The rising CO2 impairs complex strategy, while the accompanying bioeffluents degrade basic algorithmic work. This accumulation hits some demographics harder than others. Smaller, tightly sealed, low-income homes trap these bioeffluents much faster, compounding the physiological stress and cognitive damage for the people living there. Whether the impairment comes from the carbon dioxide molecule itself or the chemical bioeffluents it correlates with, the end result is exactly the same. Sitting in a poorly ventilated room actively degrades the mental capacity of everyone inside. You can measure this risk, but most commercial monitors on the market use deeply flawed technology. They use metal oxide semiconductor sensors, which blindly guess the CO2 level based on surrounding chemical compounds. A single pump of ethanol hand sanitizer can trigger a massive fake CO2 spike. The only scientifically valid method for measuring indoor air is a non-dispersive infrared sensor, or NDIR. An NDIR sensor shoots a specific wavelength of infrared light through a chamber. Real CO2 molecules absorb that exact wavelength. The sensor calculates the precise concentration based on how much light makes it to the other side, completely ignoring other chemicals. Once you measure a high CO2 level, a popular aesthetic trend suggests fixing it with nature. Architectural designs increasingly feature indoor plants and green walls to act as natural air purifiers. That idea traces back to a highly contained NASA laboratory study in the 1980s. A human exhales carbon dioxide far faster than a plant's stomata can absorb it, but the math does not scale to your living room. You would need roughly 680 potted plants to actually scrub the air. We cannot rely on cheap algorithms or decorative botany to protect our brains. We have to confront the physics of the building envelope. The only scientifically proven remediation is mechanical dilution. You have to physically push the stale air out and pull fresh outdoor air in. Modern engineering achieves this through demand control ventilation. Instead of running at a constant rate, smart building systems use NDIR sensors to read the occupant density in real time, dynamically opening dampers to bring in fresh air exactly when a room fills up. Portable air purifiers do not solve this problem. HEPA filters are excellent for capturing particulate matter and airborne viruses, but they cannot stop a gas. And commercial ozone generators, often marketed as purifiers, are dangerous respiratory hazards that damage lung tissue. For peak cognitive performance, deep sleep, and healthy blood chemistry, the biological and engineering standard is clear. We need to target an indoor concentration of 600 to 800 parts per million. Indoor carbon dioxide isn't a sharp toxic cliff, it's a gradient of risk. We need to treat ventilation as a cognitive priority, ensuring that the air inside our buildings supports the high-level reasoning we expect of ourselves.